Welcome back. Okay, so introduction to rates of change. So this is kind of probably the second chapter in advanced functions that you start doing a little bit of a deja vu and introducing yourself to the rates of change. Now, rates of change you had most likely in math, sometimes probably in grade 9, except it was primarily to do with just kind of constant changes for lines. And now, as you have done quite a few functions, and some of the functions are nonlinear, okay, so they're non-line, so they could be exponentials or parabolas, cubics, okay, so sinusoidals and so on. So now you can get into some defining new rates of change. And the idea is still that you have an input, and that input comes in, so you have an independent variable, so it's some quantity, and then that quantity you take in, it is applied, okay, and you used it for some function, and then it provides you an output, which is the dependent quantity. And rates of change is nothing else but how your output is changing with respect to your input. Now, so let's do a little bit of a deja vu of what that exactly means. How did we define it? But if you remember the concept of the slope for lines, this is not really far-fetched beyond that, except when you're applying it to functions which are nonlinear, okay, then in those cases, the actual rates of change can be different at different points in time. All right. So here's an example, okay, so that I have drawn out on a Cartesian plane. So you have your x and your y. So let's say your input and output. And let's imagine that it is linear. Okay, so it's linear. Okay, and it's going in just one direction. In this case, it's going down. And what we have is we have 2 points on this particular line. Now we can take infinite number of points, but for lines, it turns out that it actually doesn't really matter if there are infinite number of points, because what you're going to do is, if you're going to be trying to find the slope, you remember that you only do need 2 points, and then from those 2 points, it doesn't matter which 2 points you pick, you're going to get the same slope. Okay. Now, what was the slope? Well, the slope, if you recall, was basically just the change, and we used to designate the change with this little triangle, okay, so it's kind of like a delta, that sometimes we call that. So it was the change of your output y with respect to the change of your input. So as our input is changing, okay, in here, okay, what is happening to our output, okay, that's what we want to be able to find. And now for this was for lines, this famous rise over run, okay, or nothing else but simply designated as m, which was the slope. So that's what we had. And if you take these 2 particular points, okay, so you have, from here, you have basically 2 inputs. So you have -2 and let's say 3, so that's your x value, right? So we can just say that this is x1, this would be our y1, so that's our first, let's say, point 1. And then we have our second point, so let's say this is point number 2, and what we have is we have x2 and then y2. So this is what we have there. And now, how do we find this? Well, this shouldn't really strike us in any different way, except what we would do is we would just simply substitute it in, and our change within this case was just simply y2 minus y1 divided by x2 divided by x1. So that was our change. So for our example right here, if I would take that, it would have been -1.5 minus, and then I would take the first one, which was 2, like that, and then divided by x2, which was 3, minus, and this was -2. So I would have gotten -3.5 all over. In this case, this would have been 5. Now, of course, we can plug this into a calculator and then find out exactly what this is. So it looks like it's going to be negative, okay, let's say 0.7. Now, that would have been our slope. And it's independent of which points we would have picked. So, if we had different points, and say these points right here, and we did the same thing or if I plotted another point and let's say took these points, no matter what we would do, because we just have a straight line, it would always give us the same slope. And that's what we did, right? We always needed just really 2 points, and then we could find the equation of the line because it was just linear. We would find out exactly where it's crossing through the y-intercept. We need the slope, and we can figure out the rest. So this is the change. Now notice that the change could be negative right here, and that again doesn't surprise us because it just means it's a negative slope, it's going down. It could also have a positive change, right? So if we had a line which was going in this direction, so in here, what we would have had is this would have had a positive change because it is changing in a positive way. So it would have been rising upwards. So that's what we have there. Now, in general, not just for lines, but we can do the same kind of definition for rates of change. So as we're trying to do this, rates of change for any type, okay, of function that we might have. So what we would have is that our rates of change would have been with respect to the function itself. So we might have, so our output, okay, is just some function f(x). Now, because we could take any 2 points, so what we would have is we would have, let's say, maybe 1 point, which was x1, so 1 input, and we would need our y value to be the output of our function. So let's say that's point 1. And then we would take, let's say, maybe another point, x2, and we would substitute it in here, and we would get the second one. So that could be for any function, except the only difference is, now if the function itself is nonlinear, so if it's, say, a parabola or a cubic sinusoid or an exponential or maybe in log or something like that that we've studied in grade 11, then in those cases, okay, it will depend on your inputs and your outputs. So you might have different rate of change, okay, with respect to the points that you choose because your outputs will be different as well. All right, and in those cases, that rate of change in terms of trying to define this would still be the same. So I'm going to add this up in here. Let me add it. So how we would define it is we would just say that now, so our change, so this is now the change of our output, okay, with respect to the change of our input. Okay, so this is our rate of change, and this is simply, so in this case, we would write it out in this particular way. So instead of thinking of it as just simply line, we can do it for any. So let's take a look, because I want to show you these rates of change and then how they can be calculated, okay, even from something like this, which is, let's say, like a table of values. So in here, they don't even give us what the function is. So we have some input maybe, and now this input is designated with an n, not necessarily an x, and then our output is f at n. And now, so if this is 0, 1, 2, and so on, and we get the corresponding outputs. All right. So as we go on, we notice that, all right, so it looks like it's going up in some way. Now, what if I wanted to try to see, okay, to find out what the rate of change is between two particular points, okay, with respect to some output and some input that we have. Now we have many points here, so in fact we have 10 points, and I've also plotted this. So notice that this is kind of how it looks like. So I'm only plotting the actual points. And now here, let's take a look how we could find our rate of change. So if we take this, what we can do is, let's say I would take the first point, and let's say maybe the last point right here, or I guess this is my second point at 1. So this looks like it's at 1. So notice right here. So this happens at 1, and then this one right here, okay, this is at 10. Now, if I wanted to find, okay, what my change is, so this would have been like trying to find, okay, the line that goes through those two particular points. Now notice, when you do that line, it actually doesn't go through all the points. So we call this line, the secant line. Okay, so this is what it's called. Okay, so secant line. Now, that secant line can change depending on the points you pick if your function is nonlinear. And in here, it looks like it's nonlinear. Because if I would pick two different points, let's say if I would pick these points right here, so let's say if I picked this one, okay, and maybe this one, then now all of a sudden, if I tried to draw the line through these 2 points, okay, so this wouldn't really be the same. Okay, so this would kind of be changing in some way like this. So it would be slightly a little bit different. All right. Now it turns out that what I took this from, so this, okay, so the function itself is actually an exponential. So this is equivalent or equal to, okay, 1000, and then this was 1.12, okay, to the n. And that is our function. And if we would plot it, we know that this would explode on us. It would be exponential, it would be nonlinear. All right. So now these rates of change, if I took these 2 points, okay, within here, so as I said, so let's say this was one of the points, and then I was trying to find my secant line in here, okay, so that would have been the change between those, okay, so the change of f at x, say f at x, okay, with respect to the change in our x. Now, what that means is here, our x is actually n. Okay, so this is what we have. And we can try now to figure it out from these 2 points. So now my change, okay, so I'm going to take my second point right here. So this would have been 3105.85 minus, okay, the 1120 divided by, and this would have been 10 minus 1. And now I can go ahead and compute it and then see what that secant line and what the change, okay, what that rate of change would be. 3105.85 minus 1120. Okay, so that's 1985.85 divided by 9. So my answer divided by 9, and this would have been 220.65. Now, these rates of change, because they are changes, okay, for the output with respect to the input, they are some quantities. So most likely if you're measuring, now it turns out that this, okay, is actually, I kind of came out with this from the compounding formula, okay, in terms of money, okay, and n is just the number of years that you have. So this is, okay, this change comes with units, okay, so that means that this would have been the number of dollars per, okay, year, and that would have been the change. So the money is changing, okay, by $220.65 every single year, okay, if you would assume that you would only take those 2 points. But of course, if we switch the points, okay, this amount might be different. And that, okay, let me just show you, because I plotted it out for us. It's just so that you can see it. So here on decimals, okay, so here are the points that I have, and I guess I probably should have gone here from 0, just so that we include that 1,000. So that's 1. And this is just the line, and this is what we would have, right? So this is the exponential, and it kind of starts to blow up, okay, as we keep going. All right, so that's our function, okay, and I'm assuming that it's starting from 0, okay, and then it's years, okay, 1, 2, 3, 4, 5, and it just keeps going. And now I can, of course, change the elements, okay, how many I can put in here, and we will notice that actually if you take any 2 points, we certainly notice that our secant, as you keep going to the right, would have been increasing, right? So it would have been going like this, and then it would just getting steeper and steeper and steeper. So our rate of change is increasing, okay, over time, and it's positive. That's at least for this function. Now, you can do the rates of change for any function, and you can pick any 2 points that you have, right? So it can be for a parabola, it can be for a sinusoid, okay? And that is something that you most likely will do. So this is our introduction to these rates of change and trying to get us back, okay? So for linear, it's not a very big deal because it brings us back to the slope. And no matter which points you pick, you're going to notice that the rate of change is the same, okay? But it can be both positive and negative. For nonlinear functions that you have, the rate of change, picking the 2 points and trying to find maybe a through, which we call the secant line, okay, that may change between the points that you have. And that's what actually makes functions nonlinear, okay, that you have. That's one of the key features between linear and nonlinear functions, that the rates of change for linear are constant. They're not changing, they're the same. But for nonlinear, they're not necessarily constant. Now, it will, of course, depend on the 2 points you pick, because you have to sometimes be careful, okay, because you might get the illusion that something is linear. For instance, if you take a sinusoid function, which just goes up and down, and you're only picking the points that are kind of the crossings through the zero, you might think that the slope is flat, that it's just zero, but of course it is not. It's going up and down, okay, depending on that function. So that's something that you're going to go over, okay, a little bit more often. Hopefully this brings you back to the rates of change, and you certainly should be able to calculate rates of change just by watching this video and then trying it on some examples. All right, thanks for watching. Okay, we'll see you in a future video. Bye, everybody.